Ellsworth are some, at this stage, formulas that I won't go into the development or derivation of it. So for the next few set of homework, mostly it's just empirical formula for the time being, that you know which one to use and how to use them correctly. And later on, you will look at tables in the text for looking at different drag coefficient for different objects, a different Reynolds number, and how to use those tables correctly to get the homework done. But what I'd like to address right now is the formula that you will need for the homework, primarily, of which you are asked to calculate for problem 926. A car hood that assume is what, 5 foot by 5 foot, fair enough, right? Traveling at 65 miles per hour. So you have this car hood that you can model as a semi-infinite plate for all intent and purpose. I mean, if you don't believe in that, you can put in the rest of the fixture of the car, the windshield, the tire, but those are inconsequential. What the problem asks you is, over this 5 foot length, as a boundary layer developed over this hood, under this condition, tell me how thick, and I use the symbol delta, tell me how thick is the boundary layer at the location where I go from laminar to turbulent. So you have that critical Reynolds number of 500,000. You know how to calculate that based on the condition of the problem. What is missing, which I will give you now, is the formula of which you can estimate the thickness of the boundary layer. All right? Do you understand the problem statement? And for that, you can also tell us, as your homework, how far from the leading edge will that transition occur? And that's all straightforward number punching, really nothing to the problem. But you're going to find that the answer is very tiny. It's about a foot. I'm giving you the answer because Mike's going to post it anyway. It's all approximate. It's actually about a foot from the nose of the hood where transition will occur. So when you go home or on the weekend driving down 460 at 60 miles per hour, you can look at your look out your windshield, look at the hood. And you can picture about a foot from the nose of the hood. You have the immiscible. You can't see it. None of this is watchable from a naked eye. About a foot from the leading edge of the hood, the thickness of the boundary is only about less than a tenth of an inch. Tenth of an inch, you know how big that is. And beyond that, the boundary becomes turbulent. And all this concept, as I will tell you later on, has huge consequences of entering devices. Being able to know where the curve and how big the boundary is, because for an airplane or a ship or any other fluid problem, knowing the thickness, which is what you're asked to do in this homework, allow me to estimate the blockage due to this invisible layer. And most importantly, or equally important later on, I want to have a formula to allow me to calculate the drag, the shear, because that's the power I will provide to move this airfoil through air. And right now, the next 2-3 set of homework, all those are formally given to you with no justification, but 4 lectures from now, I'm going to show you a very viscous development of those equations, which ultimately allow us to come up with those formulas. And that's very intense. Yes?
When they do aerodynamics tests on like cars with colored fluids, can you see the boundary layer with that?
Yeah, only if you put some dye in the fluid, then it's only using that you're able to see, or some smoke. All right, but the layer is so thin, the answer to your question is still very, very difficult. It's just like splitting hair. You see commercial on automobile, on TV, that they release smoke, but it's mainly for the main body. To see within a tenth of an inch inside this layer is just very expensive and very difficult. So people don't usually do that. We do that in our laboratory, we're using some very advanced measurement technique, but that's like PhD work. Normally in a Ford or GM, they don't care about that much of detail. Only in research, very deep end research, people do that. Yes?
So when you get close to the windshield,
Yep.
since the windshield isn't
Yep,
vertical,
yep, yep.
how does the boundary layer change? Like, is there any like?
When you are close to the windshield, a lot of things happen is well beyond our simplified concept. For one thing, all this equation, we are assuming no pressure gradient, which near the windshield, do you think that's a good assumption? You have air washing at 65 miles per hour, and it's going to do what as it hit the windshield? Stagnant. You create a huge pressure gradient, and that changes all the flow. So if you release some smoke, the streamline is going to go up and above the windshield. There's no other way. It has to, through the presence of the windshield, and negotiate around that. That's not boundary layer. So all the concept probably will break down when you get close to the windshield. It's only further near the hood, where it's almost like a flat plate, almost like semi-infinite, and you don't feel the pressure gradient, meaning as you march down, pressure is constant, atmospheric. Then you can use all this simplified concept. In real world, so Boeing is not going to use this kind of concept to analyze the airport. It's too simple. But it's a foundation. It's something that you need to know, so that when you run a computer code, take a month CPU time to get an answer, at least you know the answer is physical or not physical, right? So a lot of background here, but what we define as the thickness of the boundary layer, and we call it delta, is if I start from the solid wall and sketch a velocity profile at a distance y from the wall, where the velocity is 99% of that of the free stream, that distance from the wall, we call it the boundary layer thickness. That's our definition of delta. Distance from the surface where velocity is within 1%. And capital U is our free stream velocity. So your homework then require you to use this formula, which I will only give you now without any derivation. And it's for laminar flow, meaning the boundary layer, or rather the Reynolds number is less than 0.5 million, of which Prento and his students have come up with this formula by nothing but pencil and paper. In about 2 weeks, this is just a preview of what is to come. In about 2 weeks, we're going to look at a viscous equation of motion from Navier-Stokes and how one of Prento's PhD student by the name of Bassis very carefully makes an assumption and we're able to solve that equation using slide rule, pencil, and paper, resulting in this equation that estimates the thickness of the boundary layer. Look, both left-hand side and right-hand side has the distance x in it. So when you use the equation, you have to account for that. That's for laminar flow. At this point, I also want to give the turbulent equation, the sister equation, because you won't need it for this homework set, but you will maybe later on. So while I'm at the thickness, I want to give you the same equation as the cousin. And that's turned out to be the inverse relationship to the Reynolds number to the 1/7. So we sometimes call it the 1/7 law. And that has to do with the fact that boundary layer is turbulent, and the analysis of the boundary layer take on a very different form. So what remained, the remaining 10 minutes, what I want to revisit, and the question was asked earlier, is what is this shear stress versus the form drag. So what is it that translates to what I call a friction drag versus that of a pressure drag, which I also call the form drag. So that's best to be illustrated by example. And the total drag force is the sum of the two. And which one is more dominating is problem dependent. So I think the best example to illustrate the two concepts is using the plate, semi-infinite plate that we talked about. The first example is where the plate is, just like we illustrated before, parallel to the flow. And there's no pressure gradient. And the flow is coming head on to the plate. And low pressure gradient, P upstream and P downstream are equal. And the flow just slide along the plate, developing an invisible boundary layer. And as a result of that, we have shear stress, both upper and lower plate along the whole length of the plate. And that shear stress, to be more scientific and more correct, the shear stress is no longer the mu times V divided by H, like the simple linear profile I showed you. It's actually more sophisticated. It's the partial derivative of the velocity versus the distance y to be evaluated at the wall of y equal to 0. And that's how we will use this definition later on in 2 weeks when we solve the Navier-Stokes equation and obtain the shear stress along the plate. For this example, because there's no pressure gradient, and dP dx is 0, we have no pressure drag, meaning the upstream and the downstream pressure are equal. There's no pressure differential acting over an area to create a form drag. Then in this extreme case, where the flow is parallel to the plate, the only contribution to drag is due to friction, due to all that shear add together. So the longer the plate, the more wetted surface, the more drag you will experience. But it's purely due to frictional effect, no pressure differential. To understand the come about of the pressure drag or the form drag, all we have to do is rotate the plate by 90 degrees. So that now the flow is perpendicular to the plate. And in this case, all that remains is the pressure or the form drag and nothing else. Let me show you a diagram as to why I can justify saying that. So now all of a sudden the plate is rotated 90 degrees. Instead of infinite plate, I just draw a finite plate, and the flow is going perpendicular. There's one streamline that hit the nose or the center of the plate, and the flow will do what? It stop. The rest of them has to negotiate and go around the plate. Any shear that create will be perpendicular to my flow direction and hence have no contribution to the drag force, because drag force by definition is parallel to the flow. And what happened when this normal plate to the flow is that behind that plate, the flow cannot completely reattach to the back of the plate. It just doesn't have that ability to negotiate a sharp corner and remain attached to the back of the plate. They get separated and creating some vortices, swirling flow. And when you have a tornado with swirling flow, what usually happens to the pressure inside that tornado? Any thought? In the eyes of a hurricane, pressure is very low. All right, so you create a low pressure right behind the plate. And if you draw a control wall, now you see the fact what is called pressure drag. This low pressure, let's say you have 14.7 psi coming from the ambient on this plate, and now right behind it drop to 7 psi. The pressure differential, 14.7 minus 7, times the area become a drag force that will try to push the plate down. So if you are driving on the highway at 60 miles per hour, you stick your hand out and you cut through the air like this, through the window, that's the first case we're talking about. All your hand feel is the shear, and that resulted in the drag force on your hand. Now you rotate by 90 degrees. You feel a lot more pressure. Your hand can go backward. That's what this is. Where the force in the flow direction, the drag force, is now primarily due to pressure difference between the front of your palm and the back of your palm, not due to shear. In reality, for most flow, spear, cylinder, airfoil, car, bicycle, it's a combination of both. Both come into play, and you have to do experimentation to find out how, for each different Reynolds number, for different shape of the object, how the drag will come into play. All right, 2 minutes and just some hints on the last homework of 9.4, where you are not given a plate parallel to the flow, but instead it's at an angle relatively small of 7 degrees. And you are given the pressure on the upper side and the pressure on the lower side. This happened to be actually negative, which is a vacuum, and this is positive. In addition to that, you are also given a shear on the upper side and the shear on the lower side, and that's given the problem statement. Out of this, and out from geometry of 7 degrees, find the lift force and the drag force. So it's a very simple trigonometry problem where how is pressure act relative to the surface? Normal, yeah, please, normal. So you have upper surface, which is a vacuum, but it's normal. So you have to resolve that by 7 degrees to the parallel and perpendicular direction of the flow velocity, x and y. So that part is relatively easy. What I want to alert you to is, and I want you to think about that, and we will revisit next time, the difference on the fluid versus the plate, force acting on the fluid, that results in the boundary layer. The shear on here is actually acting to slow down the flow. So it's in the opposite direction of the flow itself, and the wall shear acting on the plate is actually in the same direction of the flow. This is something I want you to think about at home to make sure you agree with me. When we come back on Thursday, we will visit it and make sure you understand how this shear actually acts on the fluid versus how it acts on the plate. And that's how frictional effect resulting in drag. Okay?
Hey, what's up? I need to make up that the test for
Okay.
from last week.
You sent me an email, right?
Yes.
I'm probably gonna give the test back on Thursday. That was the plan.
Okay.
I'm pretty busy until Thursday. It's got to be Thursday or Friday.
Thursday, Friday.
Yeah. So what did you say you were available then?
I